realize that we have to spill a live range, it may be better to not spill it, but instead give parts of the live range a new chance by splitting that live range into different pieces. In the early 1990s, there were attempts to take this to some kind of extreme by splitting live ranges a lot before doing register allocation in the hope that merging them would be possible using coalescing. It turned out not to work too well, and Cooper and colleagues at Rice University found that it is better to split the live range when you find that it should be split otherwise. This is done by using a so-called containment graph. So what we have here is this is not the containment graph, but it's illustrate what the purpose of it is. The live range U starts here and ends there, and of V in the loop. The live range of V is contained in the live range of U. And suppose that we allocate V a register, and then we find out that we have to spill U. Then it may be the case that we should split U around the live range of V, and that's done using this containment graph. This is an interesting approach, and I have implemented it in my C compiler as a curiosity. Okay. A different, splitting and coalescing, they are related, and a different way to do coalescing was published by researchers from IBM Tokyo in 2010. What they do is as follows. Instead of using only the normal colors, which they call real colors, they introduce a new set of colors which are called extended colors, which are not related to a real machine CPU register. The extended colors are used to determine that two live ranges might be suitable to coalesce them, and the same for real colors. Okay, so what happens when we pop a live range during the shading algorithm? We pop it from the stack and expect to find a register for it, a color. Okay, so there are four cases. First, if we find a real color which is not used by any neighbor, but used by a live range which is move related to U. That means there is a copy assignment between U and V. Then we assign this color to U, in the hope of coalescing U and V later. Okay, so if there is no such real color, then we try to find another real color, which is, for which there is no move-related other live range. Okay, so if there is another real color, unused by neighbors, of course, then we assign that color to U. If there isn't that either, then we try to find an extended color, also unused by neighbors, but used by a live range which is move related to U, and assign it to you. And if we cannot find that either, we create a new extended color and assign it to you. Okay, so what can we do with this? After we have done all the assignment of colors, that means real and extended colors, to the live ranges, and we have done the coalescing, then we can repeat this. So what we have done is to coalesce some live ranges, and of course we will not stop the coloring with extended colors because they are not useful, but we repeat this, and since we have discovered which might be suitable to coalesce, there is a hope that there will be better coalescing during the next iteration of running this version of Chaitanya algorithm. Okay, and we may decide to have a fixed number of iterations of this, and if there are extended colors left when we have run the last iteration, we have to spill or split. And in that case, do it once again, but without the extended colors. They observed a 1% improvement on a machine with 16 integer and 16 floating point registers. And 1% improvement, that's good.